In this video, we are going to define the upper and lower sum, and we'll do an example where we use these and evaluate those, find those values as we continue to move towards defining the Riemann integral. So suppose f is a bounded function on a closed interval from a to b, and then we have this partition x0 up through xn. So remember, it's a partition, so that tells us that x0, that should be the value a, and xn, that should be the value b, and then the other points, they can be any values on the interior of that closed interval from a to b. For each I equals 1 through n, we let m sub I, or m sub I of f, be the supremum of f of x, or so the supremum of the function values on some particular subinterval, right? So here, I've drawn this graph down here. So this graph, we are thinking about some particular subinterval. So imagine this graph continues on, right? So maybe it does some stuff over there, maybe it does stuff over there, but we are interested in some particular subinterval, x sub I minus 1 to x sub I. So for this subinterval, we want to identify the supremum out of all of the function values, right? So what is the least upper bound when we consider all of the function values on this subinterval? And so we see we have a greatest value right up here, and so wherever that happens to be, that value right there, that would be our least upper bound, right? And we also define this little m sub I. And for that little m sub I, that is the infimum on that same interval, right? And so for here, it is out of all of the function values, what is the greatest lower bound? If it achieves that greatest lower bound, it is that value itself, right? And so that would be the m sub I. Now those are not the upper and lower sums, but those are important for identifying the upper and lower sums. So the other things that we have, we identify the width of the subinterval, right? So what is the distance? So that width of the subinterval, delta x sub I. For the ith subinterval, it is the distance from x sub I to x sub I minus 1, the distance between those x values. And so our upper sums, they are going to take each of those widths, the width of the ith subinterval. So we take the width of the ith subinterval, and we multiply that by the maximum on that subinterval. Right? And so what that looks like is we're taking that maximum data value, we're multiplying it by this width, and so we are finding on that subinterval the rectangle that is going to for sure be an overestimate. And the lower sum, it does the same thing, only it takes that width and multiplies it by the infimum of the function values on that subinterval. And so it's going to give us a rectangle, or the area of a rectangle, that is completely below the curve. All right, so let's look at an example where we calculate some upper and lower sums. So here we have this function. I've drawn it a little. It is not necessarily well drawn, but here we have some values for this function. So our function f of x here is this. We are on the closed interval from 1 to 4, and we are going to look at this partition. So we want to find both the upper and the lower sum. So when we go about finding the upper sum, so what is our first infimum of function value? So on the first interval, we're going to go from 1 to 2.5. So we want to look at from here to here, what is the largest function value? And the largest function value there is 11. Then we want to look on the next subinterval. So from 2.5 to 3.5. So from here to here, what is the largest function value? And that is this value right there. So it is the function value, 2.375. And then we have one more subinterval from 3.5 to 4. And that the largest value there on that subinterval is going to be 5. And so our upper sum, it is going to be 11 times the width of that first subinterval, right? And so that first subinterval is 2.5 minus 1 plus 2.375 times the width of that subinterval, which is 1, 3.5 minus 2.5, plus 5, this value, times the width of that final subinterval. And if we roll through and calculate all of that, we get for our upper sum a value of 21.375. Now for our lower sums, we go back and we look on each of those subintervals. We identify the infimums of the function values. And so on the orange subinterval, the infimum is that 2.375. For that second subinterval, the infimum, it actually occurs at 3. So it doesn't have to occur at the endpoints. At 3, we have a value of 1. So I didn't actually identify this in my graph, but that is 3, 1. That is the minimum value on that blue subinterval, and then the minimum value on this pinkish subinterval. That smallest value is going to be this 1.625. So when we calculate our lower sum here, I should really call this L of f comma p. So this is a lower sum for this function associated with a particular partition. This lower sum is going to be equal to 2.375 times this width, so I'm just going to, in the interest of space, write that as 1.5 plus, so that was our first lower value, plus 1 times this width, which is also 1, plus 1.625 times this width, which is 0.5. And when we add all of that up, we get something like 5.314. So our lower sum and our upper sums, we have calculated those. Beautiful. And so what we will do in our next video is we will then think about a lower integral and an upper integral. However, let me mention one more thing before we shift there. So for the upper sums, what we've done is we said for this first piece, we found the area of that rectangle. And then for the next subinterval, we found that rectangle. And then for the final subinterval, we found the area of that rectangle. And for the lower sums, we found the area of that rectangle, this rectangle, and finally this rectangle. So we added together those purple rectangles, which were all below the curve, and to find the lower sum, and we added together the areas of the green rectangles, which were all above the curve, to find the upper sum. All right, yeah, we'll talk to you next time.